Now we will discuss about work symbolized as W. We mainly will focus on the reversible work, where we can go back from a final state to the initial state for both the system and also the surrounding, with only introducing an extremely small change. Say you have a piston and inside you have a gas with pressure 1 and volume 1, and outside you have an external pressure pushing down the gas inside the piston. Now in this case, if the pressure 1 is higher than the external pressure, we will observe expansion of the gas. And at the final state, you will get a second pressure and second volume, where the second pressure will be the same with the external pressure. Now in this case, in the beginning, the system is not in mechanical equilibrium. This is an irreversible process. At all conditions, the pressure of the gas in the system is not always in the equilibrium with the pressure of the surroundings or the external pressure. In this case, especially in the beginning, the pressure of the system is not the same with the external pressure, and this causes the expansion. And for this situation, from the final state or the second state to come back to the first state, you would need to introduce an external pressure that is not going to be small. So this is what we call the irreversible process. While in reversible process, say you have again a piston with a gas P1, V1, and you have external pressure, but you also have grains of sand on top of this piston. Now you can imagine when you take, at a time, you take one grain out, the total external pressure or the pressure of the surrounding will decrease just a little bit. In this case, the volume will go up also a little bit, and we know that volume is reciprocal to the pressure. So when the volume expands, the pressure will go down also a little bit. Now in this case, the pressure of the system or the pressure of the gas will always be the same with the external pressure. And this process can go back from the second state to the first state just by introducing an extremely small change. And this is what we call the reversible process. And the work, we can calculate it from minus P and delta V times delta V. Minus because we are considering the expansion where the system is doing the work towards the surroundings. So it's the negative sign that we have to use here. And the delta V is, of course, the volume 2 minus volume 1. Now for the case of ideal gases, say you have a gas that dissociates into two molecules. For ideal gas, we know that PV is equal to nRT. And in this case, we could also use this to calculate the work. And the work can be minus delta N RT. Given that all this process occurs at a constant temperature. The delta N will be only for the gas, so anything in gas phase, and you take it from the products minus the gas in reactant. In a reaction like this, you can immediately use the stoichiometric coefficient. So in this case, it's going to be 2 minus 1. So the delta N will be 1. So far, we have discussed several parameters like Q, which is heat, W, work, and also delta E, or the change in internal energy. Among these three, delta E is the only one that we call a state function. So a state function is a parameter that only depends on the final value and also the initial value, no matter which path were taken to establish those values. On the other hand, Q and W, they are not state function because they are dependent to the path that are taken in a process. Now I will introduce you to yet another term that we call the enthalpy, which is delta H. Enthalpy, or delta H, is basically the heat that is involved in a process that occurs at a constant pressure. So the key point here is the constant pressure. And of course, it's also a form of energy, and you use joule as the unit. Now, before we have established that delta E is equal to Q plus W, and in this case, for a process that occurs at a constant pressure, we can also write down as delta E equal to delta H plus W, to delta E is equal to delta H minus P delta V, because that is what W is. In the case of ideal gases or reactions that involves ideal gases, we can also write this down as delta E equal to delta H minus delta N RT. Again, the keyword here is at constant pressure. Now, there's also processes that occur at a constant volume instead. And in this case, delta E is still Q plus W. We know that the delta V will be equal to 0. Therefore, delta E will be the same with the heat that is involved at a constant volume, while delta H is the heat that is involved in a process that occurs at a constant pressure. And this one is very common in chemical reaction because we usually conduct reactions at constant pressure, which is normally the atmospheric pressure, which is 1 atm. Just like delta E, delta H is also a state function. More often than not, we will see that the unit of delta H being kilojoule over mole. And for instance, in this combustion reaction of methane gas, using 2 molecules of oxygen and producing 1 molecule of carbon dioxide and 2 molecules of water, this is the amount of energy that is released upon combusting 1 mole of methane. Say if you have X mole of methane, then you can multiply this value with minus this value to be able to obtain the energy needed for this certain amount of methane. When the delta H is positive, that means the process is requiring energy, and we call this an endothermic process, while if the delta H is negative, we call this an exothermic process, where the process itself will release energy. Now in this case, the delta H is also often called the delta HC, where the C is a code for combustion, because this is a combustion of 1 mole of methane. Now we also recognize what we call the delta HF, which describes formation reaction. A formation reaction is the reaction that involves formation of 1 mole of a certain substance from the corresponding elements at their standard state. Now let's define what we refer to standard state. The standard state is the most stable form of those elements at room temperature, so around 25 degrees of Celsius, and the pressure of around 1 atm. For instance, let's take a look at the formation reaction of carbon monoxide gas. So we can form carbon monoxide gas from carbon, which is C solid in its most stable state or standard state, while the oxygen will be the O2 molecule in gas phase. And you have to put the substance that you want to make to be 1 mole, so this has to be 1 mole. Therefore, the coefficient has to be 1. So the rest should follow. In this case, the oxygen should be in half. The delta H for this reaction is what we call the delta HF of carbon monoxide. And because it is at standard state, which is room temperature and pressure 1 atm, we can put the symbol of a circle on top of this to represent this standard state. Again, this circle or sort of degree like this, the symbol of degree here appearing on the top of delta HF is a symbol for the heat formation that indicates that this value is a process occurring under standard condition, which is temperature of 25 degrees of Celsius and pressure of 1 atm. Now, the delta HF of elements at their standard state will always be equal to 0. Delta HF for oxygen gas will be 0. Delta HF of carbon solid would also be 0. Meanwhile, for carbon dioxide, the delta HF will not be equal to 0, and the same goes for other molecule like carbon monoxide. So this was dioxide, this is monoxide. The delta HF will also not be equal to 0. Only for elements at standard state or the most stable state in nature.